It's called the Harris corner detector. It goes after the people who worked on this problem. HCD, if you will, okay, Harris corner detector. Harris is somebody's name. This was a paper kind of published, actually interesting, it was a conference paper. So, to just motivate, right, what we mean, okay, by this, right. So, of course, they kind of formulate it in a certain way using gradients and all, but just to motivate, right, why such a thing makes sense, let us just right, look at an image, and let me draw 3 of them. Okay. In one case, I have what is called uniform plus some noise. Okay, I am adding noise because it doesn't. I don't want it to be wanted to think that all images are exact, all intensities are exactly the same. Maybe there is some amount of noise there. The second one is actually an edge, and the third one is a corner. Okay, so uniform means what? I mean, you can think of this as some I plus some n of whatever, right? I mean, whatever 0 mean with some sigma. Right? This is something like that, some Gaussian noise, something that is added. Uniform does not mean uniform noise, okay, uniform intensity plus some noise. Edge, let us say we have got 0 here, I mean, we will just take an ideal case, okay, just to give some insights. Corner, I think I will draw them by a different color. This is the corner, right. Now, suppose I take a patch, right, some patch which I decide, some size, okay. I take this patch and move around, okay, in a sense that I kind of move around, okay. Suppose I am here at this location, let us call that some xi, yi, I am sitting there and I just move around, okay. In terms of the gradients, what do you think will happen? See, for example, the appearance of the patch is going to change, right, as I move around. It is not exactly the same, right. So, the appearance of the patch, right, is going to, okay, now let us just talk about the appearance, okay, right. I mean, no, let us not even talk about gradients, let us just talk about appearance. In the first case, how much will be the change in the appearance? Do you expect a lot of change in the appearance, or do you feel that maybe there will be just a little bit of change in the appearance? Very little, right. So, we all agree that the appearance will be, the change in the appearance is going to be minimal, okay, because most of it is uniform. So, except for some noise. What about the next case, edge? So, let us say I take a patch. Now, I move around. Yes, I began. When you are, okay, now but then would this be somewhat kind of say direction sensitive? Okay, so which way would the change be minimal and which way would the change be? So, horizontally, right. So, when you move orthogonal to the edge, you will find a lot of variation, right. Horizontally, if I could pull this patch out like this, you will see a lot of variation, but if I move along the edge, there is going to be hardly any variation, right. If I move along there, that means there is some sensitivity here, right, with respect to which way I move, okay, which means that the appearance change depends upon how I move. And if I move in a particular way, there is going to be a lot of change, but then if I move in another way, which is like along the edge, then it looks like there is not going to be much of a change in the appearance. What about the third guy? I have a patch. Oops. So, I have the corner there, sitting inside that patch. Now I move. Sagnik, what will happen now? Any direction if you move, there is going to be a change in the appearance, right, whichever way you move, because you are actually sitting at a corner now, okay. So, in a sense, right, you kind of that is what this Harris corner actually, right, tries to capture. So, at a corner, right, whichever way you move, the appearance, appearance of that patch is going to change significantly whichever way you move, okay. And that is what is essence of this, and we will try to capture it using whatever math is needed for that, right. Of course, all this is there in that slide, okay, that anyway we will upload, but this too. Okay, so then the idea is this. So let us say that let delta x and delta y represent shift in x and y directions, shift in y, x and y directions respectively. Then the change in appearance of a patch of size w can be found as C of, let us call this some C of delta x delta y, which is the change. C represents the change in the appearance. So, this let us say we compute as summation I of xi yi minus I of xi plus delta x yi plus delta y and xi yi belonging to this w, which is the size of that patch. So, what this means is that that right within that window, okay, if I move by an amount, say, right, delta x delta y, and I want to compare the patch, right, which I get with respect to right that particular motion delta x delta y, and how much is the change in the appearance. So, you can of course you play the standard trick, which is to actually take this and expand it in using a Taylor series. So, you have xi plus delta x, make some approximations now because you want something that is computable. So, you write this as I of xi yi plus, let us say, and all these are scalars now, right, you are just looking at intensities. So, delta x again is a scalar, just a displacement, delta y is a displacement. So, I am writing a scalar form plus delta x, let us say we call this as what is the notation Ix, okay, and xi yi plus delta y iy xi yi, and then you will have some higher order terms which we will ignore. What happened? Something? Huh?
Delta y, I xi plus delta x, yi plus delta y, last line.
What happened? Last line, I of xi plus delta x, oh, by, yeah, correct. Yeah, thanks. Y plus delta y is equal to this one, right, xi yi plus delta x, ix plus delta y, okay, and plus some terms, right, higher order terms which we will ignore. Okay, then what we can do is we can actually push that in here, and then we will get summation xi yi, then I of xi yi minus I of xi yi minus delta x ix of xi yi minus delta y iy of xi yi. So, if we ignore those terms, right, then this is all that we are left with. Of course, these are all, right, this approximation will have some effect, but that is okay. Right. So, okay, so I think, so what happens is these two cancel off, and you can in a way sense say that, right, what you are left with is simply delta x ix xi yi plus delta y iy xi yi the whole square summed over all xi yi. Okay, now if you expand this, okay, you can expand this now, and that will give you C of delta x delta y. So, you will get summation, these are all scalars, okay, so you get like delta square x ix square xi y, and all this ix and all this gradient, right, we should have some sort of a mask, right, to actually do that, which we have already seen. You can, I will also talk about that, but we are assuming that there is some way to compute the gradient along x and gradient along y and so on, plus let us say delta square y iy square xi yi plus 2, what is this, delta x, delta y, I x y I into I y x I y I, and that you will get. Now, can we write this in a more compact form? Right, this looks like looks a little messy. Can we write it in terms of a matrix vector form or something? This is after all a quadratic, right? So this is equal to, so we can write this as delta x, delta y, and then a matrix. What will be the size of this guy? Again delta x, delta y. So what will be the entries of this? I x square x I y I, then I x I y. I'll drop that x I y I. Okay, it's there. I y I x, which is the same as I x, because these are all scalars. Okay, so this is all like gradient at a point. Okay, so that's why it's okay to interchange the order, and then you have like I y square. Okay, this is the same as what you had, what you had here, right? This is easy to check, verify. So now this delta x delta y, right, has I mean it's independent of the I, right, because it's simply a displacement. Therefore, we can actually pull that out, and then what we will have is delta x delta y. Yeah, exactly. So summation over. So now this I will put this inside. Sorry, did you? Okay, x I y I. Then double summation I x x I y I y x I y I, then double sum, then again I x x I y I y I, and double sum I y square x I y I, and then delta x delta y, right. In this matrix, right, let us call this some R. Okay, this is called this as some matrix R. Okay. Now, what we can do is, so this I x, right, we can have, let us say, a horizontal gradient. We can have a horizontal gradient operator for this, and I y, right. So, horizontal gradient kernel or whatever, or mask, right, something you will need. So, which is maybe of the kind, right, the simplest that you can think about is maybe -1 0 1, all zeros elsewhere. This is the simplest that you can think of, or you can have, right, because they actually introduce a Gaussian averager. So, therefore, that is why they do not have list -1 -1 -1, that kind, right. They do actually a Gaussian average. Similarly, I y, right, you can also have a vertical gradient, and right, okay, that is all you need. I mean, because you just have I x I y I x square, which is simply squaring that number, and I y square, which is squaring the y gradient, right. So what this, okay, now, yeah, so I think there is just this other point to mitigate the effect of noise, the patch is first smooth with a Gaussian. The patch is first, that means the patch of size w cross w that you have, right, is first smoothed with a Gaussian. So what this means is that when you compute your I x, right, if you had a continuous case, then you are doing something like dou by dou x of g of x comma y comma some sigma s, right, call that as some smoothing, okay, capital S, smoothing applied on I at x I y I. So it is like saying that, you have a Gaussian sitting on it, and then you are doing some kind of smoothing. I mean, instead of weighting everything uniformly, you are having a non-uniform kind of a weightage coming from the smoothness through a Gaussian. Then in addition, so similarly for I y, Okay, so for IY also you have something similar. Then also to give more weightage to the point in the middle of the path, then there is one more Gaussian. So there will be some hyperparameters, okay, that come in because of all this. Also to give more weightage to the point in the middle of the patch. Middle of the patch. So what they do is, so they use another Gaussian, which does the following. Anyway, this I think this is not so relevant, but I am just writing it because it is there. So it is like minus xi square plus y minus yi, so minus of y minus yi square by some divided by some 2's, let us say sigma square w or whatever. This is not the same as the other one. This is a different sigma. And so ideally, so it's like saying that when you compute R, right? So you have something like if you call this as some say w of xi yi, right? If this is the weight that you have, then it's like equivalent to saying that you are computing your R as some w of xi yi into ix square at xi yi. I mean, okay, now these are just some smoothing operations. Okay, there's nothing to get overly worried about this. Just some smoothing, right, that they're doing just to make sure that it's a Gaussian, because then you can give importance to something in the middle, and okay, what is more okay, now typically there are some hyperparameters. Okay, sigma w is usually 1 and sigma s is 2. I mean, these are all hyperparameters, okay, of this method. But what is more interesting is the following. So if you look at R itself, right? So the R that you had, okay. Now if you actually looked at the eigenvectors of R, see, first of all, right, R is actually a symmetric matrix, right? As you saw, it's like ix square. What is it? Ix iy, and then iy square, right? So it's actually a symmetric matrix. And you know that every symmetric matrix is actually normal, right? Which basically means that A transpose is A transpose A. Right? Whenever that happens, any matrix is what is called unitarily diagonalizable, as they say. Right? If it is a normal matrix, okay. I mean, normal doesn't mean the normal abnormal, not that sense. Normal matrix. Have you guys encountered a normal matrix? A normal means something like this. A matrix is normal if A transpose equal to A transpose A. Of course, for a symmetric matrix, it automatically is true. But there are matrices, right, that are not symmetric but actually obey this. For example, if it is complex, right, let me just drop a hint. A Hermitian is equal to A Hermitian A. Have you seen a matrix like that? DFT. Sorry? No. Orthogonal will mean A transpose should be identity. That condition is not there. It doesn't have to be identity. It's just that A transpose should be equal to A transpose A. I am saying a DFT will obey this. A DFT is not asymmetric. Do you know that the DFT matrix is not symmetric, right? But then it is normal. It will satisfy this. Only thing is you should replace transpose with a Hermitian because it has complex entries, right? So this is like real. This is for a real case, but if it is complex and all, then you should be more careful. It's like A Hermitian A is equal to identity. In fact, for a this one, for a DFT, it's much more powerful. Okay, so no, you used to call it unitary. Orthogonal means transpose. When Hermitian is involved, it becomes unitary. Okay, there is a slight difference between the two. Okay, now the point is this, right? So when you have which means that this is a normal matrix, and there is actually a theorem, right, that says that every normal matrix is unitarily diagonalizable, or in this case, unitary, because everything we will just take all real numbers. So let's not worry about complex entries. So what this means is that you can diagonalize it as P diagonal P transpose. Okay, where this P transpose is identity. Okay, so all these are actually 2 cross 2. So this guy, right? So this is actually a diagonal matrix, right? So this is like 11 lambda 1 0 0, and then you see lambda 2. Okay, and where are the eigenvectors of R? This is called this is an eigenvalue eigenvector decomposition, right? Why do you call it eigenvalue eigenvector decomposition?
Because P is made up of the eigenvectors.
Yeah. So what of the P? Is it the rows of P or is it the columns of P? Columns of P, right? So you can show that if I take, let's say, the ith column of P, and if you do r times, let us say that pi, you can show that that will be equal to lambda I pi, right. That is why it is an eigenvector. So, that is why you call it an eigenvector, eigenvalue eigenvector decomposition, right. Now, the eigenvectors are of r are sitting as eigenvectors of r are the columns of P, are the columns of P, right. Now, so an eigenvector, right, what does it really represent, an eigenvector? You have a covariance matrix, right. This is R, this is like, I mean all of whatever you expect of a covariance matrix, right, this guy will actually satisfy. Now, when you have a covariance matrix and you have done this eigenvalue eigen decomposition, what do the eigenvectors really tell you? They tell what the variations are, right, in which directions the variations are from highest to lowest, right. So for example, right, I mean, so if you find that right along, let's say along one direction, you have the highest variance, right, how will you capture that? That is captured through the eigenvalue, right. So, the eigenvalue should be high for that. That is when you say that that is the most dominant sort of a component, along which the variations are the highest. So, it means that I mean, if you had points, right, which had a distribution like that, then you will say that the spread is maximum along this direction. Then probably the next spread, I mean, if it is a 2D, right, then you will say that in the orthogonal direction there is still a little amount of spread, right. This is what the eigenvectors will capture. This is exactly what these eigenvectors of R will also capture. And for us, right, it is all in terms of interpreting this now in terms of what it should reflect about my corner now, right. So what you can show is that the eigenvalues that you get out of this and then the eigenvector, it will have an interpretation with respect to the edges that you have, and when two edges meet, that is when you get a corner, right. And therefore, for a corner the eigenvalues will have a behavior of a certain kind. So, you can actually make out what point you are looking at. I mean, it is not just that it will tell you a corner, it can tell you whether it is an edge where you are sitting, whether it is a flat region where you are sitting, or where you are sitting, is that a corner, right. That is the kind of information that this matrix can actually give you, which we will see in the next class. We run out of time.
The corner should be necessarily orthogonal, or it can be at any?
No. So, the thing is, right, it need not be orthogonal. You are saying that what if I had an edge? Yeah, that is also fine. That is also fine. Because there also when you move around, right, I mean, you will get, see there what will happen is, you see, in an orthogonal case, right, you will see when you have something like this, which is actually also a corner, then what will happen is, you will get one direction along which the maximum spread is there, the other one, the interpretation will be hard. Just the interpretation will not be so easy, because the spread, right, the eigenvector will still reflect that there is an orthogonal direction in which the next spread is the highest. But if you have like this, right, then it is much more clean. I mean, then you know that, right, along one direction and the orthogonal you can associate with edges, but corner does not, that is, I forgot to tell, it does not necessarily mean that they have to meet orthogonally and all. It can also be an edge like this, corner like that.